So the sum and difference rule is really nice. If I want to take the derivative of like x cubed plus x squared, it's easy. Use the power rule to get 3x squared, use the power rule to get 2x, add them together, and that is correct. Okay? But the question is, does it work when you're multiplying? Does it work when you're dividing? Now, I'm using this simple example just to show you that it doesn't. We think, okay, well, 3x squared times 2x, is that the correct derivative? Well, if you think about it, I could simplify this to be x to the fifth, right? X cubed times x squared. Then when I take the derivative of x to the fifth, I should get 5x to the fourth. Well, that's not the same as 3x squared times 2x. That's 6x cubed. So just by using that simple example, I can see this doesn't work. And let's see. If I take 3x squared and divide it by 2x, will that get me the same as if I simplify this first, then take the derivative? Well, x cubed divided by x squared is just x. If I take the derivative of just x, I should just get 1. But 3x squared over 2x is 3 halves. So that is also wrong. So mathematicians using the limit definition of a derivative developed rules for products. This is the limit definition of a derivative with a product plugged in. And they did a lot of manipulation and they developed the product rule, which I'm going to show you in a second. And they did the same thing with quotients. Using our magical formula, they found a rule for the derivative of a quotient. Now, this is why the rule is what it is, but in the future, you don't have to worry about that. You just need to know the rule, okay? So, is the derivative of 3x plus 2 times negative 4x squared minus 3 times negative 8x? It's definitely not. Now, a way you could kind of see that, again, is to simplify and then take the derivative. But I'm going to show you how, you know what, don't spend a lot of crazy time simplifying this. You're going to use this product rule. Here's the product rule. And then we'll go back and we'll write the derivative without simplifying. If you have two functions being multiplied by each other like this, f times g, we will take the derivative of the first function multiplied by the second unchanged. Then add the derivative of the second function times the first function unchanged. I'll use f and g, but sometimes it's better if I write out first times the second, so that what I will say verbally you can kind of see. It's the derivative of the first function times the second unchanged plus the derivative of the second function times the first unchanged. So going back, I could simplify if I wanted to, but instead we are going to use the product rule so that I don't have to spend that much time simplifying. I say this is my first, this is my second. I can say that's f, that's g, whatever you want to use. The derivative of the first times the second plus the derivative of the second. Now, think about the second. Negative 4x squared minus 3. The derivative of 3 is 0. The derivative of negative 4x squared is negative 8x. Here's the second times the first. And you know what? For the most part, I'm cool to just leave this. If there was some simple simplification that I could do, I would do it. But, you know, what I would have to do is distribute. And do I want to distribute? In some situations, I actually don't. Distribution is not going to help me. So this, notice, is f prime. It is the tangent slope generator for this f. However, for this previous one, I could have distributed first. Just like with x squared times x cubed, I could have distributed and multiplied x squared by x cubed to get x to the fifth. And then I could have taken the derivative to get 5x to the fourth. I could have distributed first to take the derivative. But for these situations here, it would take me a long time to distribute. And this one right here, I can't distribute. I can't take x cubed and multiply by cos x and make it an easier function. Okay? I would have to use this new product rule. We will use it so often that it will make sense to you. All right. So instead of distributing, we're going to use this new rule, the product rule. We're going to say this is the first, this is the second. And when finding the tangent slope generator, find the derivative of the first, use parentheses in case it's multiple things, times the second, plus the derivative of the second piece times the first. Okay? Now, just going to shrink this a little bit, but the key is you don't have to simplify this. Okay? It's a long, ugly-looking tangent slope generator, but it is a tangent slope generator nonetheless. I can find the derivative at x equals 1. Okay, f prime of 1. I plug in 1, 2 minus 3, negative 1. 1 minus 2 plus 1, that's 0. Plus 3 minus 2, that's 1. 1 minus 3 plus 4, that's 2. I get a tangent slope. Now, obviously, other values plugged in would take you more time to do the arithmetic for, but you could still do it. And it's actually probably taking you less time to do those individual numerical values rather than take the time to distribute everything and to simplify this. I know in math, we always like to say simplify, 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 but in this case, leave it unsimplified. I could have simplified this. I cannot simplify this, but this is a product. It is x cubed times cos x. To find its tangent slope generator, I must use the product rule. So let's go ahead and do that. Derivative of the first times the second plus derivative of the second times the first. Do not multiply those x's together. You cannot. That x is inside the sign. You can't manipulate it with stuff outside the sign. So that gets left alone. Do not tell me this is sine x to the fourth. That is wrong. What you could do, possible simplification, if you wanted to, and this is an easy thing to do rather than spending a lot of time distributing, an easy thing to do is to factor out a greatest common factor instead of like distributing, factoring an x squared out of the first term, factoring an x squared out of the second term. Maybe you make it look like that. The only cause for simplification in this class will be multiple choice questions, where you get an answer and you do not see your answer in a multiple choice selection. And you need to potentially make your answer look like something else without, violating the rules of algebra. Doesn't matter which one we choose to plug pi into. If I'm asked to find the tangent slope or the derivative or the instantaneous rate of change of the function at pi, you plug pi in, I get pi squared, let's do it here, whatever, doesn't matter, pi squared times 3 cos pi minus pi sine pi. Now we will be plugging in pi over 2 and pi and 0 into a lot of derivatives with sine and cosine because they're easy to find and it doesn't take a lot of time to find the values. So you need to be comfortable with sine of 0, pi over 2, pi. You need to be comfortable with cosine of 0, pi over 2, pi. Remember cosine of pi is over here. It's got a horizontal distance to get to the unit circle of -1. It does not go up or down at all. There's no vertical distance. That's why the cosine of pi is -1. That's one way I remember why the cosine of pi is -1. That's 3 times -1, and then the sine of pi is 0. So this ends up being -3 pi squared. Probably would have been easier if I actually plugged in pi into this form, but whatever. We found the correct tangent slope generator using this product rule. Now, it's important to remember, don't use the product rule if you just have a constant in front of a function. Remember the constant multiple rule. If I'm taking the derivative of a constant times a function, it's just the constant left alone times the derivative of the function. So, for this guy, product rule, not necessary. Could you use it? Yes, you could use the product rule in this situation. I'll show you how you could use it. But instead, I would prefer you be comfortable with just leaving the 3 and multiplying by the derivative of sine, which is cosine. Using the product rule, you would get, thinking of 3 as being your first and sine as being the second, I use parentheses to denote like what's first and what's second. We'd have the derivative of 3, which is 0 times sine, plus the derivative of sine, which is cosine, times 3. Notice the 0 times sine, that goes away. I just get 3 cos x is the same that I get here. But this is not necessary. Just more work than necessary. Okay? However, if it's x sine x, you must use the product rule. The derivative of my first piece times my second plus the derivative of the second piece times the first. Do not multiply those x's together. If anything, write it as sine x plus x cos x. Great. Quotients. Like I showed you with x cubed over x squared, it does not work. Taking the derivative of the top and dividing it by the derivative of the bottom. The derivative is not 6x plus 6 over 2. Now, I could show you exactly why by simplifying this first. I could divide each of these terms by 2x and then take the derivative, but I'm not even going to bother because I'm going to get straight to the quotient rule. Quotient rule generated using the limit definition of a derivative. We find that when you take the derivative of something with a top and a bottom, I put f over g, or you can write top over bottom. When I verbally say things, I will say top and bottom. We get the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So using top and bottom, top prime times bottom minus bottom prime times top over the bottom squared. So, though I could simplify this instead using the quotient rule, I'll take the derivative of the top, 6x plus 6, times the bottom, minus the derivative of the bottom, 2, times the top, 3x squared plus 6x plus 9, divided by the bottom squared. Now, like the product rule, we could pretty much leave this alone. However, it is very common to be asked to simplify this, and where you need to simplify is typically the numerator. Okay, just simplify the stuff in the numerator. Now, I just want you to be careful. This minus 2, make sure you distribute this negative to everything after you distribute the 2. Either by keeping the minus and then having 6x squared plus 12x plus 18 in parentheses, and then distributing the negative, or what I actually like to do is get rid of subtraction symbols and make them add the opposite. I like to distribute the negative 2, automatically making this a negative 6x squared minus 12x minus 18. Over here we'd have 12x squared plus 12x, and then I'd be able to combine my like terms. So the 12x squared minus the 6x is the 6x squared. The 12x minus the 12x goes away. I have a minus 18 over 2x quantity squared. It's important to know that 2x quantity squared is not 2x squared. It is 4x squared. It's 2x times 2x. So just little things to be ready for with the quotient rule. Distributing the negative in the numerator, making sure when you square things, you square every term. Also make sure when you square things like a binomial, you're not telling me that this is x squared plus 4. That's wrong. X plus 2 times x plus 2, which is x squared plus 4x plus 4. Okay, good. Let's find some tangent slope generators for some functions. Top and a bottom, call that f, call that g, whatever you want. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. X squared plus 1 squared. Now, don't simplify the denominator unless it's really necessary for you to do. The best and the most simplification you're typically asked to do is to simplify the numerator. X squared plus 1 minus, this is 2x squared. So I would have a 1 minus an x squared over an x squared plus 1 squared. There's my tangent slope generator. Leave it like that. Don't distribute the denominator. It actually would look messier if I did that. For g, it's tangent slope generator using the quotient rule. Derivative of the top times the bottom. Don't multiply that cos x and that x squared together to be cos x cubed. That's wrong. Minus the derivative of the bottom times the top over the bottom squared. X squared would be squared. Now, one simple thing you can simplify here that won't take that much time is, again, you could simplify the numerator. In this case, I can't combine like terms, but I can factor out an x. So I have x, I'd be left with an x cos x minus a 2 sine x. And that'd be over, and watch how if I simplify the denominator, x squared squared is x to the 4th. I can cancel one of these x's with one of these x's, giving me an x cubed in the denominator. You'd be expected to do that for a test, a multiple choice question on a test. Can you simplify more x's? No. You can't cancel or factor out this x, which is in the sign. You can't cancel or factor out that x inside the cosine. It's only the x's in front that can be factored and canceled that make 1. Okay, so don't go any further than that. What can we do with tangent slope generators? We can find tangent slopes, or we can see when the function has a specific tangent slope. Okay, these are our application questions. We'll start by understanding instantaneous rate of change just means tangent slope. We will find the tangent slope generator. We will have it generate our tangent slope at x equals 0. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Now, understand what the question is asking me. It's not asking me for a derivative. It might be like a quiz test question that would ask me for not the tangent slope generator, but it's asking me for a specific tangent slope, which means I'm not going to simplify this because I just want to figure out what the tangent slope is at 0. I'm going to skip the simplification knowing that it's very easy for me, and I know I won't make any mistakes if I just plug in 0. -2 times -1, because this is 0, this is 0, minus, I know this entire thing on the right is 0, over -1 squared. My goodness, I was easily able to find the tangent slope to this crazy function at 0. No simplification needed, anything crazy.
What would you do to define the derivative at a spot where the derivative is discontinuous?
Good question. So like what if I asked you to find the tangent slope at x equals 1? Because like 1 squared minus 1 is 0. I wouldn't ask you to do that because f of 1 doesn't exist. So no function value. The question was about like if you have a discontinuity, what is the tangent slope? You can't find it. If you are not continuous, you don't have a tangent slope. Now, when we answer some questions in the future, we want to keep in mind that the locations of discontinuities can't be answers. Like if I ask you to find a horizontal tangent for this, and you get an answer x equals 1 for some reason doing your equation, you know that can't be the answer because I can't have 1 in my denominator. Does that answer your question? Okay. Cool. Let's do the next one. Why don't you find the instantaneous rate of change of that capital G at 0? That was pretty easy. Okay. Okay. Here we go. More application. We could find tangent slopes of functions by plugging in values into a tangent slope generator. We can find when functions have specific tangent slopes by taking our tangent slope generator and setting it equal to the tangent slopes that we're looking to find. In this case, horizontal tangent, we are familiar with this. Horizontal lines have a slope of 0. Horizontal tangents have slopes of 0. We will figure out when does our tangent slope generator generate a slope of 0. The other thing great about having a tangent slope generator. Okay, let's see. I got to find my tangent slope generator first to set it equal to 0. Go to the top times the bottom, minus 0 to the bottom times the top, all over the bottom squared. And I'm setting this equal to 0. Okay. I have a fraction equal to 0. What do I have to concern myself with? What is a fraction equal to 0? What part of my fraction needs to be 0? Just the top. Can the bottom be something else? As long as it's not 0, as long as it's a number, not 0, we're good. When we have fractions set equal to 0, I don't want you to kind of like let this disappear, because this is important. When x is 1, we will have a 0 in the denominator. That's bad. You can actually see up here, f of 1, which gives us 1 over 0, we know that that's the location of what? What kind of discontinuity? Non-removable, infinite, we got a vertical asymptote. We're going to keep that like in our minds. Like, we better not get something that has x equals 1 in it. Because if I get x equals 1, then I'd get a number, like I'd get a 0 in my denominator for both f and f prime. But whatever. So what I'm telling you is if you have a fraction set equal to 0, you just have to set your numerator equal to 0. And ignore this, but don't forget about it. Don't let it disappear. All right, I'm going to go ahead and distribute to simplify. We will have to simplify to solve these equations. So 2x times x minus 1 becomes 2x squared minus 2x minus x squared. This becomes x squared minus 2x. Factor out an x, x minus 2. I get two solutions when x equals 0 or 2. Read the question carefully. What are they asking me? Are they asking me for an x coordinate? Are they asking me for the equations? They're asking me for the points at which the function has a horizontal tangent. So, since I'm asking me for the points, I need to find the points. What is f of 0? 0. What is f of 2? 4 over 1. 4. So at 0, 0, I have a horizontal tangent. At 2, 4, I have a horizontal tangent. Read your question carefully. Make sure you provide what is asked for. If they ask you for just x coordinates, you could have stopped at 0 and 2. If they ask you for equations of tangent lines, you can't. Okay. 2 questions. One is in your notes, one is not. I'm going to make sure we do this one that is not in our notes, but this is an extra practice for horizontal tangents. So leave some space on the right of this one, because we are going to do this one, and this one is very important, especially for your homework. So those of you not in attendance, hopefully you're watching this video. Okay. Horizontal tangents, what we're doing here, again, tangent slopes generate a slope of 0. Find the tangent slope generator, see when it generates a slope of 0. Distribute that negative. I'm going to factor out 1. a negative 1, which will allow me to factor the remainder. They asked me to find the points, find the points. Negative 3 over negative 6, which is positive 1/2. And 7, 3 over 49 minus 7 is 42. That ends up being like 1/12. Divide by 3, 1/14. Cool. Oops. All right. Now, horizontal tangents, find when a tangent produces a slope of 0. Tangent slope generator generates a slope of 0. Finding where tangents are parallel to certain lines just changes what we do a little bit. Instead of finding when a tangent slope generator generates a 0, we're going to find when a tangent slope generator generates the slope of this line. Now, one issue is that I don't see the slope just by looking at it. I'm going to have to do a little bit of legwork to solve for y to visually see this line has a slope of negative 1/4. I want to figure out when does my tangent slope generator generate a slope of negative 1/4. I will take f prime, I will set it equal to negative 1/4, and I will solve. Now this will create an equation that's a little bit different than what's going on here. For these, I could just ignore the denominator. I will not be able to ignore the denominator here. So let's do this one over here on the right. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over bottom squared. This is my tangent slope generator. When will it generate a slope of negative 1/4? Don't ignore anything, because you can't. You have to simplify. This is x minus 1 minus x. So this is negative 1 over x minus 1 squared. That is equal to negative 1/4. A lot of students are probably thinking we have fractions equal to each other, we cross multiply. I don't love the phrase cross multiply. I think it confuses students. I have variables in a denominator to move them to the numerator, and I can do that by just taking the reciprocal of both sides. So just like 1 over both sides. If I do that, I'd get x minus 1 squared in the numerator here. I'd get 4 in the numerator here. I can also go ahead and just take the opposite of both sides, make everything a positive. So I end up with x minus 1 squared equals 4. We have 2 routes for solving this. One is square rooting both sides. Now, if I square root both sides, the square root of this unknown squared gives me a plus or minus x minus 1. So this is x minus 1, but it would be equal to plus or minus the square root of the right side. That is very important. A lot of students forget the plus or minus when using the square root technique. Or we could distribute and solve the quadratic by factoring. This is x squared minus 2x plus 1 equals 4. It doesn't help us to have a factored form equal to a value. It helps us to have everything on one side and have a factored form equal to 0. I'm able to factor this, x minus 3, x plus 1, and I can see my two solutions are 3 or negative 1. I could take positive 2 and add 1, it gives positive 3. I take negative 2, add 1, it gives me negative 1. So either way, I get the correct answers, 3 and negative 1. You will see a couple of those on your homework. Finally, 2 more. I need to introduce the concept of a normal. This is probably new to you, the word normal. Anybody hear the word normal before, like in a geometry class? Physics? Anywhere from like other math classes? Normal means perpendicular. In this case, it's perpendicular to the tangent. Now, you probably remember, if you have a slope that is like 3, we call a perpendicular slope an opposite reciprocal. Negative 1/3 is a perpendicular slope. That would be a normal slope. If I have a slope of 2/3, the perpendicular slope, I'll use this uppercase T flipped as like perpendicular symbol, would be negative 3/2. Okay? We are going to find our tangent slope at 0, but then we will find our normal slope, which will be the opposite reciprocal. Here we go. Tangent slope generator. I hope it doesn't give me 0. Let's see. Drill to the top times the bottom. Minus, drill to the bottom. Times the top. Over the bottom squared. My tangent slope at 0, this is my tangent slope, is 6 minus x minus 1. So this is just 5 over x plus 6 squared. That's nice. My tangent slope at 0 is 5 over 36. That means my normal slope is negative 36/5. Now for my equation of my normal line, again, y minus y1 equals m times x minus x1. X is 0, we know that. My slope is now my normal slope, which is the negative 36/5. My y-coordinate is, again, my function at the x-coordinate, 0, which is 1/6. And I would recommend graphing this and seeing that perpendicular nature of things. Okay? The last one is just a word of caution. Okay? I asked you to find the slope of the tangent here. What most students do is jump straight into the quotient rule and you get something very, very nasty. Now you can use it, but it might not be nice. What I'm trying to teach you here with this last example is sometimes look and see if simplification is actually easy to do. And in this case, it really is. After distributing negative 3, I get negative 9x plus 6x squared. I can divide both of these terms by the 7x, and watch what I get. Negative 9/7 plus 6/7 x. Do you want to find the tangent slope generator? Sure, 6/7. No matter what x value you plug in. That is a lot easier than using the quotient rule. Sometimes we don't want to use the product rule. We want to distribute. So be careful. All the problems on your homework, though, you should be using the product and the quotient rule.